In the previous video, we presented a microscopic model in which two genotypes with different fitnesses interconvert by way of mutation. In this video, we apply eigenvalue-eigenvector analysis to study the long-term genotypic population composition of the model for various values of mutation fraction. We will quickly walk through eigenvalue-eigenvector analysis, assuming that the arithmetic procedures being presented have by now become automatic. To review these calculations conceptually, please review the videos introducing linear algebra. We write an equation that we can solve to find the eigenvalues of the matrix. Remember that the minus lambdas are attached to the main diagonal elements, and that the so-called off-diagonal elements form this product. Foiling and rearranging into descending powers of lambda, we obtain a quadratic equation whose pair of roots can be determined using the quadratic formula. These are the two eigenvalues of the system, one corresponding to the plus in front of the square root, the other corresponding to the minus. Using the eigenvalues and the matrix, for example using the northern row of the square matrix, we can write an equation that determines the relationship between n1 and n2 for each eigenvector associated with the eigenvalues lambda plus and lambda minus. Algebra is fun. The coefficients of the eigenvectors occur in this pair of ratios, where we say a pair of ratios because we can take either the plus or the minus in front of the square root. Now that we've obtained eigenvalues and eigenvectors, we can analyze the steady-state properties of the population composition. Say that the fitness of blue cells is W1 equals 3, and that the fitness of orange cells is W2 equals 2. The blue cells are more fit. Suppose that orange cells can mutate, with the mutation fraction mu3 equals 0.005 toward the blue allele, and a mutation fraction mu2 minus mu3 to alleles not explicitly tracked by the model. The mutation fractions to the left and to the right are together a total mutation fraction mu2 for the initially orange cells. Suppose that the mutation fraction from the blue cells toward the orange cells is twice the overall mutation fraction of the orange cells. Hold all parameters fixed except for mu2 and, by consequence, mu1. We can explore the behavior of the system at different values of mu2. The lambda plus or minus expressed in terms of horrible gobbledygook and square root stuff corresponds to these plots. Lambda plus always floats above lambda minus. We can study the eigenvectors using a plot of the ratio of the n2 population to the n1 population for various values of mu2. Remember that the eigenvector associated with the largest eigenvalue dominates the dynamics of the system at long time, unless we are in a special situation in which the initial condition of the system can be constructed using linear combinations only of other eigenvectors. The eigenvalue lambda plus dominates for all these values of the mutation fraction mu2, so the dominant eigenvector is the one whose ratio of n2 component to n1 component is plotted in the yellow eigendemographics curve. For small mutation fractions mu2, the ratio of the population of orange cells to the population of blue cells is close to 0, meaning that the steady-state population is almost purely blue cells, those with allele A1. When mutation fractions are small, the raw fitnesses of the cells can indicate which cell type will take over the population. This is survival of the fittest. For large values of mutation fraction mu2, we are cranking up the flow from blue cells to orange cells, and also from orange cells out to the pink X. The yellow eigendemographics curve ascends, indicating enrichment in the population of orange cells as compared to the population of blue cells. As we turn on the waterfall from blue to orange, the orange population can become large compared to the blue population, even if the blue population has greater fitness. One of the lessons of quasi-species models is that dominance in a population is not determined merely by raw rates of making progeny or fitness. You have to ask whether cells are breeding true. If this is your first time through the video, you can skim the cited paper, develop your own outlines, notes, derivations, and calculations, whatever you find helpful. Then, after you have developed familiarity, Watch the video again and see whether you can address the questions that are about to appear in a 1 to 2 hour sitting. Why is it inappropriate to consider values of mutation fraction mu2 greater than 0.5? What happens when mu3, the fraction of back mutation from orange to blue cells, vanishes? Can you use the analysis in this slide deck to study that case? The ratio of the population of orange cells to blue cells and the eigenvector associated with the eigenvalue lambda minus is negative. For this eigenvector, the population of orange cells would be negative if, for example, the population of blue cells were positive. A negative cell population is non-physical. Nonetheless, we retain this eigenvector in order to analyze the dynamics of physical populations. Is it okay for eigenvectors to have negative components? Why? Scan through the green box on the cited paper. Use the cited paper or your favorite resource to distinguish between an error catastrophe and an extinction catastrophe. In the previous video, we outlined the microscopic picture in a simplified quasi-species model. In this video, we then used eigenvalue-eigenvector analysis to study the long-term genotypic population composition of the model for various values of mutation fraction. By analyzing this model, we showed that dominance in a population is not determined merely by fitness alone. It is also important to consider whether cells breed true.